Hi, this is Mrs. Myers, and we are going to start an introduction to proofs. This video is going to be the lesson for the honors class, Geometry 21, but it is almost identical to the Geometry 22 notes, so it should suffice for either. But if you're in 22 and the notes seem a little different, you can just, fast forward the video. Okay, so in class we're going to start with this little activity where you try to get cat to be dog by changing one letter at a time, but for the video I'm going to just continue on. You guys did a worksheet where you were highlighting the steps that you would take to solve algebraically. This was like a preview to what the proofs are going to look like. So in this particular case we would distribute this -2, and so our first step, like the reason for our step, is the distributive property, right? We would distribute the -2. The next thing we would want to do probably is combine like terms. These are the x's, and we would combine them, and we would get 15x minus 18 equals 12. So my reason there is combining like terms. So you did a worksheet that kind of helped you do this, and it wasn't, you might have worded things a little differently, but the same idea. Okay, and then the next thing we would do is add 18 to both sides to get the 15x on one side and 30 on the other side. And the last thing we would do is divide by 15. So let's see, we added 18. And then we divide by 15. And that's how we would get our answer, that x is 2. Okay, so that is justifying every step that we take. Is a preview, because in proofs, that's exactly what we want to do. We want to justify every single step, every piece of information that we use to logically get from one given statement to a statement we're trying to prove. So this box here in your notes highlights really the parts of a proof. You will always be given a statement that's labeled given, and it will give you information. This is algebraic. Eventually we'll be doing geometric proofs. Then you will have a proof statement. So this is kind of like your starting point is your given and your ending point is your proof. There are several ways of writing a proof. This particular proof is called a 2-column proof because the statements and the reasons are set up in like a table with 2 columns. Always start with your given first, and your reason for that is just you write given. And then you're going to follow the logical steps. You can see here, we distributed, then we combined like terms, then we added, and then we divided, and that's how we got our answer. And our answer in this case is what we were trying to prove. So you're just going to start with your given and end with your proof. Remember that your statements, the first one might be your given, but everything else needs to have a justifiable reason that is either a postulate or a theorem or a definition or some sort of property. Okay, the only time you have anything other than those things that I just mentioned, right, is the first one, which is given. You never use prove as a reason. Okay? So, just as a review, you guys remember doing the distributive property. This would be AB plus AC. Distributing the A means multiplying it to everything inside the parentheses. And we just match the signs. Combine like terms. Make sure that the x matches the x, or if it's an x squared, it goes with an x squared. You can't add an x squared and an x. Those don't match, right? Now, these properties here, most of them you are familiar with. Addition property of equality just means if you add the same thing to both sides, it's still equal. That's just, you know, when we did our steps, we added the same thing to both sides, and it remained an equation, an equal on both sides. Okay, subtracting means you can subtract from both sides. Multiplication means you can multiply both sides. And division means you can divide both sides by the same thing, and it will still be equal. Substitution might be a little bit of a different property, but you've learned this concept before. If A equals B, then B can replace A in any expression. You've done this before. If you have an expression like 2x plus 7, and then they tell you x equals 3, well, you've learned that you can replace the x with a 3 because x equals 3, right? So you would rewrite this as 2 times 3 plus 7. That's substitution property. You just took out the x and replaced it with a 3 because they're exactly equal to each other. These two properties are going to be useful in geometric proofs. One is the reflexive property of equality. It literally means if A is equal to itself. It's literally you have the same exact thing on both sides of the equal sign. It's one statement. One statement that it seems really obvious, but sometimes in geometry you have to have a statement and a reason. And A equals A is going to sometimes be something we need to state. A transitive property of equality, this one is super important. If A equals B and B equals C, that means A must equal C. Think about this logic. Let's say if I'm the same height as my mother, and my mother is the same height as my brother, so I'm the same height as my mother's the same height as my brother, well then I must be the same height as my brother, right? It's just this transitive property. It's a transition. You kind of transition through mom over to brother, okay? You'll see how that works in our proofs. So, if we have this proof that's going to be an algebraic proof, the first thing we do is we copy exactly what's given to us. We copy in the first line here as the first statement. Copy it exactly. Your reason again is going to be given. Now we just follow our algebraic logic. If we know step 1 is true, then we can logically lead to step 2 by doing the distributive property. Just think about what would my first step be in solving this. And you would distribute the 2. Reason, distributive property of equality. Well, what's the next thing we're going to do? Now, in proofs, you don't have to show the step. In other words, I don't want to put like minus 10, minus 10. You're not going to actually show the step. You're just going to show the result of the step. I know I want to subtract 10 from both sides, so on the left I'm going to end up with 2x, and on the right I'm going to end up with negative 12. I just show the result, and I justify it by saying I'm doing the subtraction property of equality. You can abbreviate POE, property of equality. Last thing I want to do, again, I'm going to divide by 2, but I'm not going to show it. I'm just going to show the result, and that's division, property of equality. Okay, so I'm going to have you try these on your own, and so pause the video and then do the proofs and check your answers when you're done. Okay, so if you just want to check your proofs here, notice the first reason is always given. Everything's justified. I put these little plus 4, that just means I added 4. That was my addition. So I did that here just so you can see and follow along, but you don't have to put that in your proofs. Okay, and you might have a different order sometimes, like especially in this second proof. Maybe you know, added the 8 first instead. Oops. So it might be a different order, but just check that all of your reasons kind of match my reasons. Okay, so this is just a recap of the definitions and properties and postulates that we've learned so far. Lots of definitions here. These 3 things are going to be used a lot in the proofs that we're going to do now. Angle addition postulate always says that, you know, one angle plus another angle right next to it equals the whole angle. That's angle addition postulate. Linear pair says a pair of adjacent angles. Oops, sorry, that's linear pair definition. Linear pair postulate says if 2 angles form a linear pair, then they are supplementary. This is really important. 2 angles form a linear pair, then they are supplementary. This is the vertical angles. Remember, this is going to become vertical angles theorem at some point. Vertical angles have equal measures. The theorem is eventually going to say that the vertical angles are congruent. Right now, we're just saying that they're equal. Okay, so let's look at some really important combinations, because this is where we start getting really particular about how those postulates and theorems are actually written. You can see, let's just go back one again. Let's start with linear pair. If 2 angles form a linear pair, then they are supplementary. The postulate doesn't say they add up to 180. The postulate says that they're supplementary. That's really important. I know it means the same thing, but we're going to get really picky when we get to the proofs about how we state these things. So notice in a proof, if you have 1 and 2 forming a linear, 1 and 3 forming a linear pair, so let's say the diagram looks like this, angle 1 and angle 3, they form a linear pair. So your statement is going to say they form a linear pair. I know this just by looking at the diagram. Whenever you're kind of looking at the diagram and identifying something, like, oh, look at that, that's a linear pair. That's going to be definition of linear pair. That statement in your proof is actually optional. Sometimes you'll see it there and sometimes you won't. The next 2 statements are not optional, right? So then you might say angle 1 and angle 3 are supplementary. That is because the linear pair postulate says if 2 angles form a linear pair, then they are supplementary. So notice this is like your if and this is like your then. The first statement, if these 2 angles form a linear pair, then they're supplementary. That's exactly how the linear pair postulate is stated. So we're justifying our logic from step 1 to step 2 by this reason, linear pair postulate. We know they're a linear pair, therefore they're supplementary because of linear pair postulate. And that's how the logic of a proof goes. Then we might, the next step might be, therefore, right? Now this kind of becomes our if. Well, if 1 and 3 are supplementary, then the measure of angle 1 plus the measure of angle 3 equals 180. Well, how do we know that? Because we know the definition of supplementary. So we're justifying the step that says we can add the 2 angles together to be 180 degrees. Notice this took 3 steps. You can't look at your diagram and go straight to adding them to 180. If you do that, you've missed a step. You have to use the linear pair postulate in there, and that goes with using the word supplementary. You don't want to go straight to your equation and say linear pair postulate. You have to say supplementary. Write it out. S-U-P-P-L-E-M-E-N-T-R-Y. Supplementary. That means linear pair postulate. Then the equation you can say adds to 180 by definition of supplementary. This is a common, progression of steps. Notice the little m's for the measure of the angles, right? Measure of the angle. If it's in an equation, you have to have that little m there to say you're adding them up to 180. All right, on this side we have angle addition postulate. This is always going to look the same. The measure of angle whatever, MRN in this case, plus the measure of another angle right next to it, equals the measure of the whole angle. Now, notice I didn't put the measure of angle MRN plus the measure of angle NRT equals and then some number. It has to be written exactly like this. You're using the names of the angles. On both sides, the equal sign when you're talking about angle addition postulate. The measure of one angle plus the measure of the other angle equals the measure of the whole angle. Then, if you're given, like we are in this diagram, you're given that MRN is 2G minus 2, and you're given that NRT is 4G minus 9, and you're given that this whole angle is 133. Now you can write an equation. 2G minus 2 plus 4G minus 9 equals 133. What we've done here is we've used the substitution property. We've taken the fact that this thing equals this thing, and we kicked that one out, and we replaced it with that one, because they're exactly equal to each other. You'll see in proofs, when we use the substitution property, somewhere in this proof, we would have to have a statement that says the measure of angle MRN equals 2G minus 2. You would have to have that actually in your statements. This is just a partial proof shown to you here to highlight the fact that the angle addition postulate has to have the names of the angles first, then you can substitute the values and use the substitution property. Okay, those are just some common combinations. All right, so some quick geometric proofs. These are kind of like partial proofs where we're justifying our reasons, our statements with our reasons. So if it says angle 3 and angle 4 form a linear pair, then 3 and 4 are supplementary. Our reason is going to be linear pair postulate. Okay, that linear pair postulate is the one that says the word supplementary. Number 2, if angle 5 and angle 6 are complementary, then the measure of angle 5 plus the measure of angle 6 equals 90. Well, here's our key word here. We don't have a theorem or a postulate. We're just going to use the definition of complementary. What does complementary mean? If you looked it up in the dictionary definition, it says that two angles add up to 180. So we can use that as our reason in this case. Number 3, if angle 7 is a right angle, then the measure of angle 7 equals 90 degrees. Again, this is just a definition that we know. We know the definition of right angle is that it equals 90 degrees. So we're going to use definition of right angle. Given this diagram, which right away I look at my diagram and I can see that this is looks like an angle addition postulate, right? Angle 8, measure of angle 8 plus measure of angle 9 equals the measure of the whole angle ABC. That's angle addition postulate. Given the diagram below, measure of angle 2 equals the measure of angle 4. Right now we are just stating this as vertical angles are equal. Eventually it's going to be the vertical angles theorem and it's going to say it's congruent. Right now they're just equal. So if we try a full proof using geometry, this is, in other words, this is not just an algebraic proof, this has actual geometry statements in it. Okay, so it's telling us the measure of angle 1 is x. Again, we want to label our diagrams just like we've done in the past. Label your diagram with the given information. That's always the first thing to do. Let me write that here so you don't forget. Okay, now what kind of angles are 1 and 3? They're vertical angles. So after our given statement, this is an optional step, but you could say vertical 1 and 3 are vertical angles, and that's just you look at the diagram and you recognize what they are. That's just definition of vertical angles. Then you could say the measure of angle 1 equals the measure of angle 3. because vertical angles are equal, something that we've learned. Again, eventually that'll be the theorem, but not yet. Now we're trying to prove that measure of angle 1 equals 56. We know that the measure of angle 3 equals 56, so we can kick out in this equation, we can kick out the measure of angle 3, get rid of that, kick it out, and replace it with what we know is equal to it. Measure of angle 3 we know is equal to 56, so we're going to replace that with a 56. We're going to keep the other side of the equation the same, and sure enough, that turns into what we were trying to prove. Again, we don't want to write prove as our reason. We need to justify how we got from here to here. And since we kicked one thing out and substituted it with something else, it's the substitution property of equality. Okay, I'm going to stop the video here, and the next video will be more practice with some proofs.